manure treatment before. There we go. Um, and welcome to those listening to the recording. Um, so this is the, kind of the technical approach here. So essentially we're using Gauss's theorem, and, the idea is the flux inside of an enclosed loop is equal to everything kind of coming and going. And so, as we walk around a manure system and collect these concentration data, we can use this kind of modeling effort to get at a flux rate, right? And so, here's sort of, the formula, right? There's some constants in here, density of air, plume height. Then there's these concentration measurements we're making, and then we're really accounting for sort of directionality and wind, right, to get at this. And thanks especially to our collaborator, Eric Liebensberger, who's really kind of adapted this model from some of the work he's done on landfills to our manure systems research. So to simplify it, right, I'm kind of more of a visual guy. We're basically walking around a manure storage with a localizer. And as we go downwind of the area source, we get into this kind of peak methane, and then we go back upwind and we get down, right? So we're doing 10 laps. So each lap is sort of a peak. We have that all GPS pinned. If you do this kind of work, I recommend a good GPS logger. We've had a lot of trouble with like lousy GPS data. It's super frustrating. Then we're integrating kind of on-site wind. And, through that, modeling, basically, we're getting an estimated flux rate, mass per hour from each one of these systems. And we've been going out to 12 plus farms and really going out monthly since, about 2 years worth of data now. Those farms represent a series of different kind of management practices. So from just no treatment, sort of raw manure, just using solid liquid separation, screw presses in our region, to digesters and separation, and then even a couple of farms that are mixing food waste in with their digester systems. In addition, we're collecting all sort of this metadata, right? So we're sampling, looking at manure characteristics before and after all these treatment steps. We've rigged these temperature loggers out on these floats, so we've got sort of the shallow end and deep end of our manure storages here. And then, just spending a lot of time out there kind of evaluating what's happening on the ground. And so through that process, we've been able to sort of establish kind of baseline emissions, right? So what you see here are 4 different farms, collaborating farm 1, 2, 3, and 4. And the grayish colored bars are our estimates of emissions using the IPCC approach, specifically Andrew Vanderzag's MCF calculation tool that really lets you kind of get this at a monthly step. So there's some assumptions in there, and we've tried to really take what we know about the farm and its management and the amount of manure and kind of model as best we can. And then in the green bars, what you see are our actual measurements. So, in some cases we have, relatively good matching, CF4 maybe is a good example here. In other, spots we have weird data where it's really high, really low. So a lot to kind of dig into here. This CF4 farm is one that we've really kind of put a real concerted effort into getting at more data and have done some additional measurement efforts that I'll talk about as we get through this. But one takeaway here, and really if you look at CF4, we've got the models are predicting in our region kind of a peak emission in August, but we're actually seeing emissions higher even back into October. And so this is that same farm with a few more months of data included. And so again, you see this kind of peaking earlier in the model than in observed, but really cumulative emissions are pretty similar, right? We're not like off by orders of magnitude here. So it's interesting, and it's also reassuring that the models are close. We think that lag might be due to actual temperature differences, right? So IPCC is taking air temp and just kind of using sort of an offset, sort of a lag in temperature for the manure. And so you can see this is the observed air, and then this estimated would be what goes into the model. But then this in blue is our observed measurements. And so you can see we're kind of a little slower to warm up and holding heat in these manure systems later into the year. And then when you get a drawdown, we get some weird data sometimes. But the other thing, I showed one farm that had really low emissions, and this is something that's also got us pretty excited. So this farm happens to be using a couple of different manure additives. They're using a tremendous amount of gypsum in their bedding, And then they're also using this digestant product. And so Joel, who had a poster yesterday, this is his experimental system. We've got 12 of these tanks, and we're actually starting to kind of look at additives. And some of his first work is can we model what this farm's doing, or sort of replicate it experimentally and see are the additives the reason that we're getting lower emissions, and what is sort of the mechanism behind that. There's also just sort of management opportunities, and especially for our smaller herds, a digester, even separators are out of reach, right? We really don't see separation on any farm less than about 600 cows. You need three-phase power, you need a facility, right? It gets expensive. But so, can we just manage manure a little differently to keep emissions down? So this is Andrew van der Zag's model again. And so what we've done is model this for 1,000 cow farm scenario. So you could just scale it to 100 cows, 10 if you want. So it's essentially organic matter in. So you see this starting empty basically throughout 1 year. You see it going up. You see it sort of flattening off here. It's not that cow numbers have changed, but you're getting that biological degradation of the carbon midsummer. And then as you get cool again, that slows and you start to get this accumulation. And then on the bottom is the production of methane. In this case, it's in cubic feet. And so you can see, again, as our carbon is degrading is when we're generating most of that methane. So I would say typically we have sort of this big drawdown of manure in April and then again in October, November. When we plug that into the model, we see this reduction in solids, but we don't really reduce methane a whole lot, right? Because we're really pulling that manure out when the storages are cooler and aren't generating as much gas. So then we've run the model again where we've just said, hey, what if we just kept the storage empty all summer, right? Storage is really important maybe for winter. Maybe we can find ways to manage that manure in the summertime and have less emissions. And when you do that, we can drop those methane levels down. We do have some producers in the state that are really getting good at managing their manure and have been able to keep storages empty pretty much all summer. In our experimental system, we haven't had great examples of that, but we did have at least one farm did a big drawdown in September. They had a bunch of land open up. And so on the top is manure volume in gray, and then in red is the storage temperature. And then down on the bottom are our measured emissions in pounds of methane per hour. And so you can see when that manure was drawn down, which we have pictured here, in September, we had basically no measured methane. What's interesting, though, is they transferred in 1.5 million gallons the next month, and it's still a warm time of the year. It was coming in from another storage, so it was already sitting out in the sun, and you see those methane levels just shoot right back up again, right? So again, I think in our region, we're seeing kind of these peak emissions maybe a little later than what models predict. So yeah, maybe even it's best to target that, or if you're thinking about like that acidification additive treatment, right? Maybe targeting a little later in the summer and not spending money early in the year. The other thing to think about with this is N2O emissions. So we have used the same approach to look at that gas a couple of times, still have some data to look through, but when we do measure it, it's typically when we have a lot of these solids built up on banks, not really when the pits are full of liquid. We don't really get much N2O. So reduction potential is separation, right? So this is remaining solids in the liquid fraction after a screw press. And so these are the farms we're working with now, kind of showing average data of theirs over a couple of years. And so, we can remove anything, like 40, 50%, sometimes even 60% of the solids with these presses, or sometimes a bit less. And it really depends on the management, right? I'm trying to make solids for bedding. I want a dry solid. I'm not going to remove as much of that material. I want to just cut volume in my pit and have some manure to move to far off fields. I might be removing a lot more solids. So again, we can this is an average sort of across the farms, right? And we can do that same modeling exercise where we've got our baseline and then we have our reduction. So, it's almost a proportional, less organic matter in the pit, less methane. So this is the data from those farms. And so what we did with this model from Andrew van der Zag, again, using the IPCC methodology, is we just sort of reduced the volatile solids input to get those estimates, and then measured, in this case, are in blue. So again, I mean, we have some months that seem really high, but then other months where we have some good congruency. And then, again, some systems that seem to just generate a little bit less methane. We can do that same exercise with anaerobic digesters, right? So in this case, they're degrading those volatile solids. And then in all the cases where we've studied, there's that additional separation afterwards. Um, and so, this is where, we scratch our heads a lot. We could model just the digester impact here. Um, but then, we also could think about it this way, because does the digester remove the more degradable solids and then the solids left are just less likely to be converted to methane? Or is it more of this spectrum? I think we have a lot of questions there, right? So, are all volatile solids created equal or not? And I think I saw a few posters here today, folks, or yesterday, starting to kind of think about this degradability question. We've got a little bit of data there too, but some work to be done. Here's our digestate emissions. So same deal, modeled in gray and in orange is measured. And so, again, we have some farms where we have good matching, and we have others with these high months in the cold part of the year. If you see this picture, this is a smaller storage that's after digestion that the farm kind of uses to get solids to settle. But it's blowing off tons of methane. It's just totally covered in foam. And I think part of the issue there, not only have we set up that manure for generating gas through a digester, but we're also holding temps in some of these all winter long, right? They're staying really warm in these uncovered storages. So maybe those would be priority pits to get a cover on and capture some more gas. So yeah, this, I think, we're correcting for volatile solids. We'd like to see this, okay, here's raw, here's separation, here's combined. This is 1 month's worth of data. These are the two with food waste. But in reality, it's kind of all over the place, right? There's not such a clear treatment effect here. I think there's a lot more to kind of figure out. And we've got like a whole other year's worth of data to kind of dive into. Just as I wrap up, there's a few just other things we're getting at. So in that model, one big assumption is how high the plume of methane is. So we have a drone that actually has a 4-pound gas analyzer on it, and we've been able to sort of start flying over these storages. And so we are seeing the plume height is around 5 meters, and we're measuring it around 2. So we're pretty mid plume in our measurements. That's good. We're doing these cool flights to really look spatially at that. One thing I'll just mention here is we are thinking in wintertime, there's a little bit more buoyancy of that gas. It's warmer, and it does seem like the plume height's a bit higher in the winter. So we're doing some work to look at that. We can do the spatial variation. And then we're, as next steps, right? We're trying to get this first manuscript out with sort of the methodology and our code to go with it so other folks can start to use this. We got this backlog of data we need to crank through. Starting to pair with continuous measurements, so boreal lasers here. Do we need to rebrand this methane stuff? I don't know if you haven't read the headlines, Cornell's in the hot seat right now. And I think really, where I'm at is, despite all these challenges in funding, and it's time to stay focused on the work, right? This stuff is still important. Yes, we might need to rebrand, but I think these efforts are needed. Our producers in New York State want to do this. Like we heard from the panels this morning, they see some advantage to getting that data and to showing that they have a lower carbon footprint milk, right? So, just with that, I'll say thank you.